Now you can hold this if you're gonna walk around, or you can leave it on the desk if you're just gonna stay there.
Okay.
But let's see. Sure.
Zoom.
We're on Zoom.
Good. Sit it down and use this trouble.
I think this is everything. All right, let's see. Hello, everybody. We are just about to get into our last presentation session for the 20-minute talks. So thank you all for joining us, and here's Connor.
All right. Hello, everybody. My name's Connor, and I was working at NSO this summer with Dr. Andrea Dierke, and we were studying the evolution of an active region filament. All right, wait, it's not working, James. Have to come back up here.
Yeah, that should be good.
How's that? All right, good, perfect. All right. So some background. An active region is just part of the sun that has strong magnetic field activity. And filaments are these clouds of dense plasma that are seen in the solar atmosphere. And they appear as these long, dark structures on the solar disk, as you can see in this image here. And the reason they appear as dark structures is partially because they're absorbing radiation from the photosphere. But also, the main reason is that their temperature is a lot lower than the temperature of the surrounding plasma. And so yeah, this image here shows some large filaments. And there are actually three different types of filaments. So the first is an active region filament, which is just a filament that's located in an active region. Then we have quiescent filaments, which are filaments located outside of active regions. And then finally, we have intermediate filaments, which are kind of in between. So for this project, we're focusing on an active region filament. And I should also note quiescent filaments are a lot larger and typically last a lot longer than active region ones do. So why study filaments? The reason filaments are interesting is that sometimes they erupt. And when this happens, it influences the space weather between the Earth and the sun. And variations in this space weather can lead to events such as coronal mass ejections. And when CMEs hit Earth, they cause a lot of problems to important technologies such as satellites, GPS signals, and power grids. So here's an image from the ESA that just kind of explains all the effects space weather can have. And so the purpose of this experiment is basically to try and understand what causes these filaments to erupt. And we do this by investigating the overall evolution of the filaments. And in particular, we're interested in seeing how the filament forms and what causes it to begin to decay. So the filament that we selected to study is located in the active region NOAA 12792, which you can see right here. And at this time, there's actually two active regions, but we were focusing on the one on the right. And the filament was present from the 13th through the 22nd of December, 2020, for a total of 9 days. And we selected a reference image of the 17th of December at 1600 hours. The reason we chose this as a reference image is because we have high resolution data at that time. And so for this experiment to study the region, we constructed animations of the active region. And these animations basically show the time that the filament was present, so 9 days. And each image in the animation follows 1 hour after the previous image. So there's a total of 216 images. And we're using these animations to kind of look and see if we can better understand the supply and transport of plasma within the filament. Uh-oh. Something happened again. All right. So here's an animation of, this is a different filament that was taken, seen on the 4th of July of this year by the Gregor telescope, which is the largest solar telescope in Europe. And so this is just an example of what an animation would look like. And in the middle, you can see there's a pore right here. And then this is the filament surrounding it. It's kind of weirdly shaped. So yes. So for our data, we took it from two different places. The first is the Solar Dynamics Observatory, or SDO. This is a NASA satellite, and it contains 3 different instruments. We looked at 2 of them, the Atmospheric Imaging Assembly, or AIA, which you can see up here, consists of 4 different telescopes. And then also the Helioseismic and Magnetic Imager, which you can see here. That just has a single telescope. Between these 2 instruments, we can see the sun in 13 different wavelengths. 11 of them are from the AIA, and 2 of them are from HMI. And for our project, I should note, we only looked at 2 wavelengths from AIA and then 2 from HMI. So here are the AIA, the data that we're looking at. This is a reference image from the 17th of December. And so here on the left-hand sides, we have overview plots. So this is just the full disk data as taken by the instruments. And then there's kind of a little white box surrounding the active region. Then on the right-hand sides, we have a zoomed-in view of the region. And these are the images that we were using for the animations. So for the 171 image, 171 angstroms, this is in the extreme ultraviolet range. And it's studying the corona. In particular, it's the quiet corona. So that's a temperature of about 600,000 Kelvin, although other parts of the corona can get up to 1,000,000 Kelvin. And with 171 angstroms, we were primarily looking at iron 9 ions. And so it's very good for seeing what we call corona loops, kind of these bright arc things right here. And corona loops are basically just plasma following the magnetic field lines in the active region. Then on the right over here, we have the 3 or 4 angstroms. So same idea here, except still in the extreme ultraviolet range, except now we're looking at the chromosphere and the transition region, kind of like the border between them. So upper part of the chromosphere mainly. And the temperature is a lot cooler here, down to about 50,000 Kelvin. And we're looking at helium-2 ions. And the bright areas here indicate an area that has a higher density. So that is where the filaments are located. And you can actually kind of see this is the filament that we're looking at right here in the area with higher density. So here's the HMI data. On the left, we have the magnetogram. And this is just looking at the magnetic field strength from our line of sight. And these black and white regions are areas with higher magnetic field activity. And it's also important to note that the black and white regions have opposite polarity. So the white ones are positively charged and the black parts are negatively charged. And then on the right, we have the HMI continuum images, which is sometimes called the intensitygram, basically just looking at the surface of the sun. And here, sunspots and pores will appear as dark regions. You might note there's nothing here right now. There's actually no sunspot in this region, which is kind of strange. Usually sunspots are associated with magnetic fields. There are several pores. You can't see any in this image really, but some do show up in the animations. So next I want to talk about reprojection, which is a process we have to do. So the HMI and AIA instruments actually have a different spatial resolution, with HMI getting about 0.5 arc seconds per pixel and AIA getting 0.6. So as you can see, the HMI data is quite a bit bigger. And we also have this weird noise effect on the edges. Also, the axis is rotated 180 degrees. And this is because the HMI instrument is upside down relative to the AIA on the SDO telescope. So when we're trying to make an animation of this region, we want to align the data. And we have to do this by reprojecting. So basically, reprojecting is essentially you're transforming each pixel in the HMI image to the reference frame of, in this case, the 171 angstrom image. And when you do this, you end up getting an image that with the HMI that has the same size and orientation as the 171 image. And when we're constructing an animation of the region, we want to reproject all of the images to a single reference image so that it tracks the active region as the sun is rotating. So if you don't do this, you're just going to have like a box and the sun will rotate through it, and you won't actually be studying the active region. You'll just see the sun rotating pretty much. So reprojection is very important for the animations. And then here we have HMI contours. So this is the magnetogram data over plotted on top of the AIA images. So here it's only taking the stronger magnetic field parts, so ranging from 150 to 1,000 Gauss. And you can see that the coronal loops begin at one region of this certain polarity, and then they go to a region of opposite polarity on both sides. And then the 304 image, sorry, it's kind of hard to see, but the black and white is overplotted. You can see the filament is located right in between two regions of opposite polarity, and we call this the polarity inversion line. And filaments are typically located right above the polarity inversion line. So here are the animations of STO. In the top left, the 171 wavelength is good for seeing the flow of the plasma. And then an important thing to note on the bottom here, if you watch this area, the white and black will kind of combine, and then they will disappear. We call this flux cancellation. And flux cancellations that occur near the filaments, that is what we believe caused the decay of this filament in particular. You can kind of see spikes up here too, where the flux cancellations are happening in the 304 wavelength. Also, the intensitygram, it's not too interesting, but every once in a while you can see some pores pop up. So there are some small pores in this region, but no sunspots ever show up. So the SDO is good for analyzing the actual active region, but if you want to see what the filament looks like itself, it's not great, and we have to change to GONG data, which is the Global Oscillation Network Group. Mackenzie talked about this a little bit already, so I won't go too much into detail, but there are 6 telescopes at different places around the world. They're all ground-based, and the goal of GONG is to have 24-hour imaging of the sun. And we're not using them for helioseismic data, but we're just looking at the H-alpha line. H-alpha has a wavelength of 656.3 nanometers, which puts it in the near infrared range. It's actually the brightest hydrogen line in the visible range, and it's used a lot in astronomy, not just for solar physics. But when we are looking at the sun in the H-alpha line, we're looking at the chromosphere, which is exactly where the filaments are located. So as you can see, it's very good for seeing filaments. This is just from a couple of days ago from the Cerro Tololo telescope. So yeah, I guess I won't talk too much about this, but yeah, this is just a list of the 6 different telescopes. They're all located in very remote places, usually on a mountain, and you want to have a very dry climate so that there's minimal light pollution and the atmospheric effects aren't too strong. And that's just an image of the one in India. So as I mentioned, GONG has 6 different telescopes, so we're actually getting multiple images at each timestamp. And for the animation, we want to select the highest quality image. And to do this, we use a technique called median filter gradient similarity, or MFGS. This is a 3-step process. It was first described by Deng in 2015, then farther developed. My mentor is actually a co-author on a paper in 2018. And then this diagram kind of describes the process. I'll talk about it a bit more in detail. So the first step is to apply a median filter to the original image. So here's an example of a median filter. This is the original, and this is the filtered image. The point of a median filter is to reduce the noise in the image. And essentially what it does is if you have a very bright or very dim pixel, it replaces that with the median of the surrounding pixel intensities. And this is just an example of what it looks like to reduce noise. I didn't show the actual H-alpha images here because it's kind of hard to tell the difference with those, because most of them are actually pretty high quality. So the second step is once you have your original, which you call the raw image, and then the filtered one, which you call the processed image. So R and P, that's what those subscripts are. You want to calculate the gradients of each of these images. And to do this, we just use Pythagorean theorem. We know the gradient in the X and Y direction. These are known operators. And you can simply calculate the gradient with this formula. And then once you have that for both of the images, you want to find the similarity between them using this formula here. And that value is the MFGS value. So that's going to give you a number between 0 and 1. And in theory, the closer to 1 that this value is, then the higher quality of the image is. And here's just a scatter plot. So the y-axis is the MFGS values for all the GONG images I was looking at. And you can see they're all pretty high quality, the lowest being about 0.9. It's also important to mention, though, MFGS is not a perfect technique. It can account for things like weather. So for example, in this image, this had the highest MFGS value of any image in its region, but there are clouds. So we don't want to use that for the animation. And so unfortunately, you have to go through all your images first and filter out the ones that have clouds. You have to do that manually. And then once you do that, then you can use the MFGS technique. Another thing you have to account for with H-alpha images is limb darkening. So this is an optical effect. You can see it here. It causes the brightness to gradually decrease. So the center appears really bright and the edges, or what you call the limbs, appear really dark. And so yeah, it's shown here. And this just happens because of optical depth and the temperature gradients in the sun. Actually, it doesn't just happen for the sun, it happens with all images of stars too. But definitely in the sun, and basically the optical depth decreases as you go radially outward. So it's essentially infinite at the center, this point O, and then it decreases exponentially as you get to the edge, and then eventually at the edge it'll be 0. So it causes the outsides to appear very dark and the insides very bright. And this is problematic because you don't want to have these intensity variations when you are making an animation of the region. So to account for limb darkening, we want to make an average profile for the intensity. And we do this using polynomial fitting. So this equation here is the intensity as a function of this parameter mu. All mu is it's the cosine of the heliocentric angle, which is the radial distance from the center of the sun times pi over 2. And here's a plot. The blue stuff is the data from the intensity plotted against mu, and then this red line is the polynomial fit. The original work used a 4th order polynomial, so that's what I'm showing here. We actually found that a 6th order polynomial worked better for this data, but this one's the 4th order. And then the idea is once you calculated this average limb darkening profile, you want to subtract it from the image, and it gives you a much better looking image, which you can see here. So this is our original before any limb darkening correction. You can see it's not great. And then in the middle, looks quite a bit better. However, we still have these strange ring patterns. It's a bit hard to see, but there's like a ring here where it's darker and then it gets lighter and then darker. And we also don't want these variations in intensity either. And it's another process to eliminate those. In principle, it's like the same idea, except now we're fitting them with these things called Zernike polynomials. But in practice, it's much more intense to account for this sort of intensity variation. For example, it took about 10 lines of code to correct for the limb darkening and over 75 lines to account for these ring patterns here. But once you have done that, you get a pretty nice looking image here. And those are the ones that we want to study. So kind of to wrap up, so my computer did not have the greatest processing power. I had to switch computers halfway through, so it wasn't really able to handle the limb darkening corrected animations. So rather than show a very blurry, uncorrected animation, I thought it would be a better idea to show a sequence of just a few H-alpha images that are corrected for it. So here on the left, this is starting on December 16th. And then each image after follows 24 hours later, exactly 24 hours later. And we end on the 20th of December here. And combining this with our animations that we have of the SDO data, we can conclude that there are actually two filaments. So there's a primary one that I showed in the 304 angstrom wavelength, and that was located on the polarity inversion line. And there's actually a second filament up here that appears on the border of the active region. It's actually quite a bit bigger than the primary filament, but it shows up later, so that's why it's called the secondary one. And then from the HMI magnetogram and the H-alpha animations, we found that the small scale flux cancellations that occurred near the filament are likely what caused it to begin to decay. And then another thing of note is counterstreaming flows are this phenomenon that was observed in some other filaments right before they started to decay. And that is something that could be studied in future work. Here's an example of what counterstreaming flows look like. This is a different filament that my mentor was studying in 2011. It's a quiescent filament and it's actually really big. So these things moving here are counterstreaming flows. It's just plasma moving in the spine of the filament. And it's traveling in opposite directions like here and here. So that's why it's called counterstreaming flows. So for future work, we want to compare our SDO and H-alpha images with high resolution data from something like the Dunn Solar Telescope. And we want to search for counterstream flows in the high resolution data. And in particular, we're looking to see if there's a connection between these flows and the decay of filaments. And another thing that we can do is we can try to make segmentation maps, which is basically extracting the filaments from the H-alpha images. So here's an original H-alpha image. And then after the filaments have been segmented, that's what these white things are. I worked a little bit with this. I didn't get too far using a technique called thresholding, but my mentor went a lot more into it using machine learning, which is what you see here, because that turned out a lot better than thresholding did. So that is something that if we had more time, I would have liked to get more into. And yep, so that's segmentation maps are good for future work. And then you can like overplot the filaments on, for example, AIA data to learn more about exactly where the filaments are. And that's about it. Here are my acknowledgements. Thank you.
All right. Any questions? Oh, hand. Oh, you're up.
So I'm just a little curious, going back to your, I think it was mu versus intensity graph.
Yes.
You said that you used, your best one was a 6-order polynomial fit. I'm just wondering, like, a little curious on if you tried non-polynomial fits, like Fourier series or anything like that.
Oh, no, we did not. I think, yeah, some other fit probably wouldn't be great here. We did also try going up to like 8th order polynomial fits, and that was too much, so that didn't work out. So I guess I didn't really try, but I don't think it would work great.
Any other questions? All right, awesome. Round of applause. All right, and then next will be Caroline. You okay?
That was on, yeah.
Hold it kind of like down here
instead of not to my mouth.
So it won't
That'd
be
be a
like
good
super
idea.
loud.
Don't want to blast anyone's ears. Okay, can everyone hear me? Yes, awesome. All right, so my name is Caroline Emery. My mentor this summer is Michael Chafin. We are working through the Boulder Solar REU at LASP. My project is titled Inferring Solar Lyman Beta Line Center Brightness from Band Integrated Lyman Alpha Brightness, Correlation Studies with SOHO, SIMR, and Implications for the Emirates Mars Mission. Lengthy title, it's okay. By the end of this, you'll probably understand what everything means in it, hopefully. So let's start with the research question. What exactly do we want to answer here? And we are asking if we can infer Lyman beta line center brightness using measured band integrated or total Lyman alpha brightness values at Mars. If you also don't understand any of these words, I'm going to explain them, give you some context for that. So ultimately, we want to develop a proxy for Lyman beta, and a proxy is just a quantitative tool that lets you estimate what you care about from what you have. So we have measurements of Lyman alpha and we care about Lyman beta. So what are Lyman alpha and Lyman beta? So they are spectral lines of hydrogen, an electron falls in energy levels, so 1 level for Lyman alpha, 2 levels for Lyman beta, back to the ground state, resulting in a photon emission. And why exactly do we care about these spectral lines? We care about these spectral lines at Mars specifically. So what's happening is from the brightness of, say, Lyman alpha, we want to get hydrogen densities in Mars's upper atmosphere. And from that, we can also look at hydrogen escape rates, which would give us information about present day water loss on Mars. And to get those values of hydrogen densities and escape rates, we need a model and the brightness of the sun at Lyman alpha and Lyman beta that the Mars hydrogen can see. So what exactly does it mean that Mars hydrogen can see these spectral lines? Well, you can imagine that there's a cloud or a fog of hydrogen around Mars. And if we took a picture of this lovely little hydrogen cloud, we would see those bright lines of Lyman alpha and Lyman beta there. So it's like Mars is putting on glasses and it's looking at the hydrogen and it can only see those 2 wavelengths. It's not going to pick up any other information there. And so if we want to say, find out the total amount of hydrogen in the fog, every single piece, we need Lyman alpha and Lyman beta in order to determine that. So we have a MAVEN image on the left that kind of shows this hydrogen corona, and then the image on the right shows sort of that hydrogen corona at the 2 wavelengths we care about. So Lyman alpha is on the right at 121.6 nanometers and beta is on the left at 102.6 nanometers. All right, so where these wavelengths are in the solar ultraviolet spectrum. So we have one here. We have wavelengths on the bottom, and then on the y-axis, we have a brightness. So you can see Lyman alpha is this nice big spike, stands out from everyone else, really easy to see. There's not too much happening near it. Lyman beta is this tiny little dip in the bottom between this carbon and it looks like oxygen there. It's hard to see, it's very small, it's not as bright, and there's other stuff happening around it. So if we wanted to zoom in and look at these wavelengths specifically, we can see here, this is the shape of those wavelengths. They're very nice shapes. Then, so analyzing these shapes that we have here is, if you take the area under the curve, so this entire area, and this is a section of the graph that I zoomed in on, there is more stuff to the left and to the right. So we're taking this area under the curve for the entire line here. You get that band integrated brightness, which is that total brightness. And then the line center brightness is quite literally just the brightness at the center of the line. That's the wavelength we care about. This is where, say for Lyman alpha, where 121.5-ish nanometers is sitting. That might be like 121.4 or 6, somewhere in that range. So we are looking at units of photons per centimeter squared per second for that band integrated brightness, the area under the curve, which is going to tell us how many photons are passing through a 1 centimeter squared area. And then the line center brightness has the same units, but it's specific to a wavelength, photons per centimeter squared per second per angstrom, where that angstrom is 121.5 nanometers. So I get my information and my data from SUMER, which is an instrument on SOHO, the Solar Helioscopic Observatory. And this is full disk solar data. So I'm getting an image of the entire sun, every single piece of it. SUMER usually points at a single spot on the sun, but for looking at Lyman alpha and Lyman beta specifically, we're not too concerned with a single spot. We want to know about the entire sun. So here's the satellite here, and then we have SUMER is one of the many instruments here, and then here's a fun little graphic that shows you what happens. Here's the front of SUMER, and then here's the back of the satellite in case you got confused. Here's the sun. So what happens is you can see the field of view of SUMER is not pointed directly at the sun. So you get a bunch of light here, and it bounces in to the instrument, and you get a full picture of the sun. And how do I know what is full disk data I'm using? The short answer is I grabbed the dates from a paper, Lemaire Plus 2015. They already found this information for me, so I went ahead and made use of that. If I wanted to, I could also find this information myself just by looking for the points where SUMER is not pointing at the sun, which should be easy to do. I think the limiting factor would be whether or not SUMER actually took measurements of the wavelengths I care about when it's pointed off the sun. Let's go. Okay, so now you have some context right? So can we infer Lyman beta line center brightness using measured band integrated total Lyman alpha brightness values at Mars, right? So we're back to looking at Mars here. So imagine instead that this is information we get from Mars about Lyman alpha. We take that area under the curve, that band integrated brightness, and just only from that information can we get this dotted green line for Lyman beta and get Lyman beta's line center brightness. Okay, so this is what I did to get my data, which is grab Sumer files, get the data that I want, plot some graphs, integrate some graphs, make some more scatter plots, and then I want to calibrate the information that I have as well. So data comes from the Virtual Solar Observatory. It's a fun little website with just a ton of information about all kinds of satellites and instruments on there. You can narrow down your search parameters to spectral range, date, time, great place. And then we end up with these bits files here, which have a ton of headers with information in it. So the wavelength and mean spectrum values I used come in bins. So there's 1,024 bins. Each bin has one value assigned to it. And then from those bins, we grab an array for the wavelengths and we grab an array for the mean spectrum. So this is what that Sumer data actually looks like once you get those arrays out of there. So you can see that this is a slit spectrograph here. You can tell because there's a nice bright line at the center. And this is on a logarithmic scale. If I had not looked at this logarithmic scale, you would really just get these bright parts here. So that's why you can see different colors and a bit of noise happening in the background. So Lyman alpha is really easy to identify, super bright. It looks like it's essentially the only spectral emission that you're picking up there. Maybe there's one to the left, not too sure if it is or not, but just looking at that, you could say that's Lyman alpha. Lyman beta is a bit harder to see. There's other things happening in the area. So if you think back to that solar ultraviolet spectrum I showed you and how small Lyman beta was and how crowded in it was between carbon and oxygen. Could be carbon and oxygen here, probably not. It's probably something different, but the main idea is that Lyman beta is not easily identified on the slit spectrograph. So then I download my wavelength arrays here. And so I plot wavelengths versus the mean spectrum. It is not aligned when I start. It's all over the place, but it's kind of nicely together. And basically the method for this was I say, okay, here's that line center brightness that I care about. And I grab a line center brightness for every single file and subtract it from its corresponding wavelength. And what that does is say, okay, your line center brightness is 121.5 nanometers. This is now the center. So here's 121.5 at this 0 value. And every step to the left or step to the right is just another value that is some distance away from the wavelength we care about. I repeated this process for Lyman beta 2. And so if we want the total brightness of Lyman alpha and Lyman beta, you have to integrate, get the area under the curve. So that is what I did from this nice lined up graph here. And then I plotted that versus lizard values. And lizard gives us a correct brightness in a sense. So Sumer also gives us a brightness, but it's okay, not amazing. So we want something to compare it to that's a bit more trustworthy. And for the integration, I used Riemann sums for a discrete integral, taking the midpoint of my mean spectrum, and then the height is going to be wavelengths. I think I got that backwards. Summing rectangles, great way to take integrals. So Lizard is the LASP Solar Interactive Solar Irradiance Data Center. We all work at LASP. I hope you know what LASP is. That's us. We did this. They have a lot, like 106 data sets. It's a trustworthy source. We can, put a little more trust into their measurements of what they say a correct brightness is. And then the last step here is going to be calibrating my Sumer brightness to this correct Lizard brightness. And then we grab information from time C to get the correct brightness for Lyman beta. Correct. All right, so current work. So here's the lined up graph here. And then there's that integration I did, except this time I'm plotting it against a time scale. So area under the curve translates to here. right? And then let's see. So the top scatter plot shows the lizard values versus time, which is the total solar brightness here, our correct brightness. And then Sumer also says, hey, here's a brightness that we think we have. And you can see they are vastly different in terms of order of magnitude. We have, 0.02 versus 4 times 10 to the 11th of lizard versus time. So if you want to calibrate this Sumer data, you need a ratio. So you take a ratio of the lizard value, the correct, over the okay value of Sumer versus time. What you get is just a value, R. Arbitrary units, doesn't matter. This is our ratio. So if we take these numbers here, multiply it by everything here, then we get this, which is what we want. A nice correct value. We do the same thing for Lyman beta, and you'll notice that there are not as many plots for the time C. That's because the instrument just launched really recently within the past 15 years. So it hasn't been taking as many measurements. Sumer has been, or SOHO has been up since for I think 26 years. So it's supposed to be up for 2 years. It's been out there for 26 years. So it's a very long mission. And then again, we have that same idea where we have a correct brightness, a brightness that Sumer says we have, and then this ratio again, and it's the same process. Ratio times Sumer gives us a correct brightness. So in the future, what I would like to do in the short term is fix those time scales. So the data that we get for the full disk information, it's just random days. There's no like organized, like every 5 days, every 10 days, we're going to get data for this. So it'd be nice to have an evenly spaced time scale. I also would like to do those calibrations, which is easy. I already have the ratio. So all I need to do is multiply it times my Sumer integration. That's all done. In the long term, we want to replicate these figures here. So this is from that Lemaire plus 2015 paper, and this is looking at Lyman alpha. So here's that band integrated brightness versus Lyman alpha's line center brightness. We want to do this horizontal axis, the band integrated brightness of Lyman alpha versus the vertical axis here, the line center brightness of Lyman beta. We'll start using that Sumer data first. Eventually, after that gets done, we'll do a regression analysis. So maybe a linear fit y equals mx plus b might be a good one, especially considering that Lemaire already did that, where x is going to be that Lyman alpha measurement, and this is going to be the measurement at Mars. End goal, Lyman alpha measurement at Mars, and then the y, the output is going to be that Lyman beta line center brightness. And for acknowledgements, I would like to thank my mentor. I would also like to thank Aaron and Bethan for helping me out and meeting with me all the time and answering my questions. My friend Adam for helping me with my code, and to the NSF for giving us the grant money. Any questions?
You can keep that one.
Okay, I'll keep this one.
I'm gonna take this one.
Sounds good.
Wait, so there's no feedback when it turns on. All right. Any questions? Okay.
So very nice talk. I don't know if there's any reason that you might expect a different sort of correlation between Lyman alpha integrated and Lyman beta line center, but if there was, what would be the most likely other option?
Maybe like an exponential increase could happen just because, so right now the shapes, I suppose, if we're looking at these integrated subplots, doesn't appear to be completely linear at the moment. So I'm hoping that doing that calibration from, let's see, that ratio back to lizard and spacing out the time scale might give me some more insight into that. But yeah, I also don't think we wouldn't get a linear fit either, but it's always a possibility.
All right. Any other questions? All right, round of applause. Press it down, it should turn off. That off. Jeez. Yeah. Thank you. All right, so I'm gonna break that microphone. We're gonna go on a break, 10-minute break, actually a little bit more than that. And we're gonna start back up at 2:05. So for everyone online, 2:05 Mountain Time. So thank you. There, and I believe there will be coffee. I'm not 100% sure if it's fully set up yet, but that'll be right outside this room. Thank you.
Welcome back to the last leg of our 20-minute presentations. Thank you all for coming again, and all our virtual attendees as well. We're going to be starting with Aislinn today, right now. So, are you ready? Okay, fantastic. We'll get this set up and then get going. Alrighty. Yeah, we'll put you with a. Let's see. So I'm going to give you this.
Okay.
Which
Didn't watch any other ones.
no, that's okay. So you can hook this anywhere on
Okay.
your probably like around like between midway.
Like here.
Yeah, that's perfect. That should
Okay.
do it. So then I'm going to turn this on,
Okay.
and then you can just hold it. Don't clip it to you because
Okay.
the clip's down. But let's see. Then right here. Oh, so arrow keys or space bar,
Okay.
and yeah, you're good to go. There's laser pointers right there.
Ooh, that was so funny.
So
Oh, okay. Hi, everyone. My name is Aislinn. My mentor is Professor Lynn Kistler at the University of New Hampshire in association with Dave Brain's Mock Center. And my project has been on auroral substorms and ionospheric outflow. Specifically, how ionospheric outflow changes during auroral substorms. So the first matter of business is to define what a substorm is. This is a phenomenon that occurs when magnetic energy has been accumulated in the magnetotail, and then it gets released through reconnection and driven into the ionosphere. You can kind of see that here at the diagram on the right. The plasma sheet starts to thin, there's high energy protons flying around, and there's convection driving energy towards the Earth. This energy is the same energy that drives ion outflow, so we naturally expect ion outflow to increase during substorms. What I specifically was looking to do is compare the different phases of the substorm and compare how ion outflow varies between methods of identifying a substorm. The reason we care about this sort of stuff is because the outflow of heavy ions like O+ can really change the dynamics of the magnetosphere, and it can affect technology in space like satellites, but also technology on the ground like electrical grids. If we want to talk about bigger picture science like the overall habitability of a planet, magnetic fields and atmospheric loss have a huge role in that. And so understanding how these pretty common events can affect atmospheric loss and ion outflow is really important to understanding the whole puzzle. So how do you identify a substorm onset, also known as the start of a substorm? We consider this the start of the expansion phase. So when it goes from just being really high energy in one spot to expanding around the auroral arc. The first and really the best way of doing this is by just taking pictures and looking for where it initially starts to brighten. And we'll go over an example of this on the next slide. The other most common method is to look at the average changes in data from ground-based magnetometers. There's this super fantastic project called SuperMag, and it has a bunch of different lists that use over 120 ground-based magnetometers to collect this data and identify substorms. The last method is to look at dispersionless particle injections at geosynchronous orbit, which isn't a method I looked at this summer, so we won't really be talking about that. So this first image you see here is actually a collection of images from the UVI instrument on the polar spacecraft. You can see right about at this middle panel here, and everyone after that, things start to get brighter and brighter and brighter. And you can see it starts to move more and more towards the pole in each image. That is how you identify a substorm with images, by looking for where it initially starts to brighten and where that brightness starts to expand polewards. These other plots you see here are using the magnetometer method. I specifically want to draw your attention to the blue parts of this plot where it has a really sudden dip. When we see that really sudden dip occur, that's what we consider the start of a substorm using this method. So, what methods did I use this summer? The first thing I did is I compiled and compared lists of substorms that used both imager and magnetometer methods. I looked specifically at a 3-month time period from December 1996 to February 1997. The reason I looked at those dates specifically is because we wanted to validate our methods against this pre-existing Wilson study. Once I had all of those lists, I performed a superpost epoch analysis on each list using TEAMS data from the FAST spacecraft.
A superposed epoch analysis is a technique where you line up similar events at a key time and then take the average. So I lined up auroral substorms from 30 minutes before their onset to 90 minutes after the onset, and then took the average of their ion outflow for that whole time. TEAMS is a mass spectrometer aboard the Fast Auroral Snapshot Explorer, also known as FAST. This operated from 1996 through 2009, and its primary objective was to investigate the plasma physics of auroral phenomena on Earth. Once I did that for that 3-month time period, we started to slowly expand our time range outwards. So these are a few images from the Wilson study we wanted to compare our methods against. This first image you see here shows the location of everywhere that teams took measurements during all of these substorms. The reason this is important is the same reason why it's important to have multiple methods of identifying these onsets. Spacecrafts can't be everywhere taking pictures of everything all at once. So you have to understand where your data is coming from to better understand what the data gaps are and the information it's actually giving you. This other plot here shows the results we wanted to approximately get when we did it on this list. This first panel here shows the O+ outflow, and the bottom panel shows H+ outflow. The solid line represents larger substorms, and the dashed line represents smaller substorms. So, what did we actually find out? The first thing I did is I took this Wilson substorm list and I compared it to 4 other lists found on the SuperMag database. And we were expecting a much better match than we actually found. The best match was with this Conlu list, and they had about 66% of matching substorms. The reason this still isn't a great match is because these are both imaging lists. So they used the same data from the same instrument on the same spacecraft for the same time period and only had 2/3 matching. When we compared this imaging list with the magnetometer list, we found that there was only about a 20% best match when we were expecting much, much higher. So this caused us to ask, well, which list is actually best? Which is most accurate, specifically within the imaging lists, because that's the easiest to verify. So I spent a few days looking through the polar UVI images myself to try to determine which list is better. What you see here are 2 collections of images from 2 substorms that were on one imaging list, but not the other. And as you can see, they're pretty similar. There's not a clear reason why these would be rejected from either list. They have similar brightening patterns, similar expansion, similar auroral arcs. So we weren't able to tell which list, if any, were actually better. That's what drove us to do the superposed epoch analysis on all 5 lists. Because if you don't know which one is best, we'll just have to run the analysis and find out. So the first list that we ran this analysis on was the Gordon-Wilson list. As you can see here, this better shows what a superposed epoch analysis really is. Together, these plots combine 127 substorms. We lined them all up 30 minutes before onset to 90 minutes after onset, and these were our results of their ion outflow. This is a better way of visualizing the data because it not only tells us where the mean flux occurs, how big the mean flux is, but it also shows us how good our data coverage actually is. This allowed us to be able to pick out some bad data and some bugs in the code. And so based on these plots, after several iterations of the analysis, we decided this was finally the results we were looking for to be able to apply this to the 4 other lists. The first collection of plots you see here are from the Conlu substorm list. This is the list that was the other imager, and it had the best match to the Wilson list, hence why it looks the most similar. Right next door to that, you see the analysis for this Newell list. And as you can see, they look pretty different despite evaluating the same thing for the same time period. You come away with these plots with a different idea of how substorms affect ion outflow. I want to draw your attention to the top panel of these plots specifically. You can see on the REU substorm list at onset, there's a sharp spike in outflow. That's what we were expecting. But when we look at the Newell list using the magnetometer method, we actually see the opposite, where there's much more outflow before the substorm and not nearly as much as we were expecting at the onset, where it actually decreases. These are the 2 other magnetometer lists we ran our analysis for. And overall, we found the same thing. We don't see a sharp increase in outflow at onset. We generally see more outflow before the onset than we do at onset. This caused us to ask, well, what could really be affecting our analysis? What could be affecting the averages, and how could we visualize our data better to see if this is actually the truth behind what's going on? So we decided to break all of these substorm lists up into large and small substorms, similar to how the Wilson study did. We did this using something called the KP index. This is a measurement of the disturbances in the magnetic field, and ultimately we use it to tell us how powerful a substorm is. We used 2 as our cutoff value, so anything that had a KP index of 2 or below, we called it a small substorm, and anything with an index of 2+ or above was a large substorm. Once again, we wanted to compare our results to the pre-existing Wilson study. So this first set of plots you see here, we've seen it before. These are the outflow results for the Wilson study. Right next to that are the small substorms as categorized by our method using the KP index. As you can see, our plots, especially in the top panel again, don't look all that similar, and overall we found a much lower ion outflow in our results. Looking at the larger substorms, we found just the opposites. I especially want to draw your attention to the scale on the side of these plots. The large substorms, as Wilson categorized them, only goes up to 2 × 10⁻²⁴. For us, it goes all the way up to 5 × 10⁻²⁴. The reason it's surprising these are so different is because out of 127 substorms, there were only about 10 or 11 of them that switched from one list to the other, so we wouldn't expect it to have this big of an effect on our outflow. This led us to believe that there are probably just a few really powerful substorms that are completely throwing off our average. And we want to establish a study where our results don't vary wildly based on just a few data points switching lists. So we decided we need much more data so that we don't just have 1 or 2 substorms throwing off the whole study. We wanted to expand from this 3-month time period into a 2-year time period. We also decided that we wanted to filter out substorms that occurred at the same time as a geomagnetic storm, just because we didn't want anything from the storm itself affecting our analysis. Once again, we wanted to divide into larger and smaller substorms to see how those affect things differently. So far, I've gone through all 5 of our lists. I've separated out the data that had substorms occurring during a geomagnetic storm, broke it into large and small substorms, and I started to run the superposed epoch analysis for this, but as you can imagine, 3 months of data is a lot smaller than 2 years of data. So I don't quite have the results for that yet, but hopefully soon. In the future, we want to be able to run this superposed epoch analysis for all non-storm time substorms for the entire FAST mission. Like I said, this mission operated from 1996 to 2009, so it covered an entire solar cycle. With this, we would be able to evaluate the role of the solar cycle, the seasons, and the strength of the solar wind and magnetosphere interactions, and see how all of these things affect the ion outflow during substorms. This will give us a bigger picture idea of the role that substorms actually play in atmospheric loss. With that, I have a summary slide of the most important things we talked about today. Determining the onset of auroral substorms is pretty subjective, so different lists have different onsets for the exact same time periods. And it's abundantly clear that magnetometer methods do not agree at all with imaging methods. I ran a superposed epoch analysis from December 1996 through February 1997, and we found that the maximum ion outflow did not occur at onset for all of our substorm lists, unlike we had anticipated. It's apparent that a few large substorms are completely throwing off the average in this study, so really we need to expand to a larger time period in order to understand what's actually going on. With that, I just want to say thank you to everyone who took the time to listen to me today, and if anyone had any questions, I'd be happy to answer them. Any questions?
So can you go back to the slide that has Wilson versus a small versus large? Not that one. Can you go further down the slide?
Yeah, this one?
No, keep going. Sorry.
You're good.
Okay, that one.
Yeah.
Yeah. So can you explain a little bit better why it seems to be in the second graph on the right? Middle one is more looks like more kind of like the first half. So like the trend is the trend, it doesn't seem to follow suit well, like the two, I don't know if you're trying to explain the similarity between them, but the top blue line seems to diverge compared towards the end versus rather than follow suit or similar to the red line. So is that expected or is that not expected?
For the differences between the red and the blue lines?
Correct, yeah.
Yeah, so the blue line represents H plus ions and the red line represents O plus ions. We found in this study overall that our oxygen ion outflow was actually a lot lower than we had anticipated as well. We think that this is because the time period we looked at was during a solar minimum, and since oxygen is much heavier than hydrogen, it takes a lot more energy to increase that outflow. As to why hydrogen suddenly dips off like that while oxygen increases, we frankly don't have a very good answer for that. Before we try to quantify the physics behind anything, we really want to be able to expand our time range because it seems like there's just a few weird substorms that are affecting everything strangely.
Sure, thank you.
Yeah.
I have two questions, if that's okay.
Yeah.
It was a great presentation too. by the
Thank
way.
you.
So the first is when you are like when you're expanding your time range, you're excluding substorms that happen with geomagnetic storms. I was curious, like on what basis are you determining that a geomagnetic storm is happening?
Yeah, we used something called the DST index. It's kind of similar to the KP index, but it has more correlation with geomagnetic storms than substorms. So anything that had a DST index of -20 or lower, we categorized as a geomagnetic storm, and we took that out of our data.
Cool. And then I just had a question about like how you showed in the summary slide to reiterating the point that the magnetic methods, the magnetometer methods don't agree with the imaging methods. I was just curious, like, it's like to you, does it seem like it's not just that they don't agree, but that the magnetometer methods are like under detecting things, or is it just like literally that the overlap between the two methods is so small?
We think what's actually happening is that the magnetometer methods are over detecting. Because when you look at the imager lists, the maximum number of substorms we saw was like 230, but the magnetometer lists went up to 600 or 700. And there's a lot of things that can affect magnetic field readings, but there's not a lot of things that will cause the aurora to suddenly appear if you're taking a picture of it. So we think we're getting a lot more false positives with that, which is disappointing because it has more data coverage. So ideally that would be more accurate. Yeah.
Hi, I just had a brief question. You mentioned earlier that the plots are based off solar minima. And so I was wondering, what do you expect that during solar maxima to find very different kind of plots than before, or again, I don't know if you know anything about that.
Yeah, I think we expect when we're looking at more of a solar maxima, just based on the physics, we expect there to be more ion outflow overall, especially of the oxygen, since that's heavier and it can be a little bit harder to get outflow with that. In the sort of preliminary runs I've done of the larger time range, that includes more solar activity, it does seem like the hydrogen and the oxygen are much more similar in their outflow, but it's too soon to say for sure how that's going to affect things.
Thank you. Any other questions? All right, another round of applause.
And then, okay, this is gonna clip. And have you clip this here first? Just like people have been putting it like kind of on that, yeah. And then you'll have this on you.
Or set it down, because if you set it down, don't. Because bad things happen. I will tell you, for whatever reason, the space bar sometimes doesn't work. So you may need to just click on the slide or like click on this arrow button. Yes. Cool. Thank you. Whenever you're ready.
Little bit of sneak peek. Hi, everyone. I'm William Solorio. My mentors are Dr. Amy Merkel and Dr. Brink. And this is understanding the variability of neutral calcium in Mercury's exosphere by comparing messenger observations to models. So we begin our study of Mercury with a very basic but important question about life. Life, as we know, requires water in order to exist, but for water to be on the surface of the planet, it needs an atmosphere. Here we reach an interesting point. We can go two ways. We can say that magnetic fields are therefore required for planets to be habitable, that magnetic fields protect the atmospheres. Laws such as Lorentz force tell us as much, but simple physics also tells us that having a magnetic field increases our cross-sectional area in space, meaning that we interact with solar wind more, and that can lead to atmospheric loss. So we're at an impasse here, contradiction. Do magnetic fields protect atmospheres, or do they have no impact? This is the core foundation behind the Mock Research Center, which my mentors and I are a part of. And Dr. Amy Merkel and my work in the group is to figure out how Mercury ties into this question. But why consider Mercury? Well, Mercury has both an atmosphere and a magnetosphere. When I say atmosphere, I really mean more a very thin atmosphere, kind of like the moon. It's referred to as an exosphere, and it's also surface bounded, which means while the particles are not very likely to collide with each other, they can collide with the surface of the planet. So by having a surface-bound exosphere and a magnetosphere, we can study the atmospheric loss processes on Mercury, isolate these processes, and figure out the connection between having a magnetic field and whether it protects the atmosphere or not. We can learn what we can apply what we learned from Mercury to other planets, which makes Mercury a really good case study for learning these different processes. I keep mentioning these source processes on Mercury, and well, I referred to them before as atmospheric loss processes, but for Mercury, they're source processes. They're what create the exosphere and maintain it. They are photon stimulated absorption, ion sputtering, and impact vaporization. Photon stimulated absorption is pretty much when the solar photons break the bonds of surface material and release it as gas into the atmosphere, the exosphere. Ion sputtering is similar. It's when ions collide with the surface of the planet, and that collision releases the material into the exosphere. And then finally, we have impact vaporization from interactions with interplanetary space dust or meteoroids. Basically, the heat and energy of these collisions results in both materials being vaporized and released into the exosphere. So now that we know that these different source processes behind Mercury, I want to bring to attention these three graphs. These were created using observations from the Messenger space probe. And what's fascinating is that these processes are constantly occurring on the surface of Mercury. And they actually result in different spatial distributions of the different species that are in the exosphere. We notice that the distributions are different for sodium, calcium in the middle, and magnesium. I want to bring attention to the one in the middle, calcium. We can see that a lot of the calcium is sort of centered around the dawn hemisphere of the planet. This can be explained by some of the source processes that I mentioned earlier, but what Messenger also did, and I'll explain the plot here for a moment. This is taken in the Mercury-Sun plane. So if you look at the sun, that points directly towards it in that plane. So Messenger not only took observations here, but also took some on the polar cusp, polar region, which you can see very well. There it is right there. It took observations here, and we noticed some enhancements that can't really be explained. We don't know why we saw those enhancements, why we saw a lot of calcium there. And that research leads us to the research question: how do we explain the observed enhancements of calcium over the dusk northern pole of the planet? To answer this research question, we took the methodology of which contained two different components. The first component was taking the observations we had from MESSENGER, specifically over this polar cusp region, and making a plot out of it. And the second included making a model, a simulation of the calcium exosphere with different source processes active. In particular, we looked at the dawn source process and ion sputtering. You may ask yourself why use a model and not just study the observations we had from MESSENGER. That's because our polar scans are very limited, and we can isolate the different source processes with the model. Let's talk about that first component that I talked about. Here I have a picture of Mercury with its magnetic field and MESSENGER's orbit. Notice how it's a north-south orbit. It takes us to the North Pole and then all the way down to the south, where it's farthest from the planet. And I want to highlight this point, farthest from the planet, because the spacecraft was able to get a lot of its good observations. Because it's moving the slowest, it's farthest away from the planet. It took two different types of scans: day-side limb scans, night-side sweeps. And the way the instrument did this, UVVS, which is ultraviolet invisible spectrometer, was at this low point beneath in the southern region of its orbit. It looked at attachment points to the equatorial plane and then took radial scans for the day-side limb scans, and then at the same point took tail sweeps for the night side. Once we had this information for each scan, we specifically programmed, NASA specifically programmed the spacecraft to look at different wavelengths for the different species that we expected. For calcium, we expected a wavelength of 402.7 nanometers. So we had a different range around this wavelength, and we counted how many photons were at that wavelength, and then fitted a solar spectra to that plot to remove that solar background. But once we had this, and after doing some math, we get the radiance for that one scan. Once we have that radiance from the scan and go back to the picture that I showed earlier, we're able to plot and learn more about the different spatial distributions of calcium. I mentioned before how there's some explanations for why calcium is different to sodium. And that's because sodium is more, I guess you could say, it's more impacted by solar radiation pressure and photon stimulated absorption, while calcium, since it's this side of the planet, dawn side, is the leading side, and it's moving through space, kind of like when a car moves through rain, the windshield collects the most amount of rain. This side of the planet collects the most amount of meteoroid collisions. So that's why we can maybe see this enhancement in the dawn side. The interesting thing, though, is that we also see an enhancement in the polar region of the planet. Here's a better picture. As I mentioned before, we have a limited amount of scans of this polar region, and we could theorize that maybe because this is a magnetically active region, talking about the cusp here, maybe ion sputtering could be causing this enhancement, or the dawn source impact vaporization could be trickling up here and causing this enhancement that we see. But there really is no way to know unless. Here's a different picture of what the enhancement I'm talking about. But there really is no way to know unless we test the different source processes. And here's where the Monte Carlo simulations I mentioned earlier comes into play. So the routine, which was developed by Dr. Matthew Berger, essentially takes in your initial conditions, which are packets, which represent atoms, species you want to create a model exosphere out of, in this case calcium, and some initial conditions, that whether that be specific location on the planet you want to model, where all the source is coming from, etc. And of course, the source process that we want to isolate. Since this is a Monte Carlo simulation, it solves the equations of motion for each of these trajectories. Since that's a differential equation, we use a fifth order undercut integration method to solve those equations of motion. And we get the trajectories of the calcium. Once we have the trajectories, we can actually, this is the model, this is the simulation of the exosphere. And we simulate messenger going through this exosphere as if it had actually gone through it, like it did in the actual messenger mission. The conditions that we used for the model, specifically for the dawn source, were we assumed that gravity and radiation pressure were active. We assumed that there was a sticking coefficient, which meant that if the model calculated that a trajectory were to hit the planet, it would just stay at the planet when it bounced. And then we have a Maxwellian speed distribution and surface spot spatial distribution. Both of these are really referring to the fact that we're looking at the dawn source source process. And then a temperature of about 60,000 degrees Kelvin. This is a very energetic source that we saw for calcium. That plot there is a two-dimensional plot that we could make with some of the observational data that we have from the model. But instead of making a two-dimensional plot, what we did was make a plot comparing the radiance of the instruments, as I mentioned before, and the model that we have, exosphere. This is for orbits 2,961. We're just comparing the dawn source to the messenger data. And if you see here, that solid line on this picture here, that's the path that messenger took or would have taken in our model simulation. It's going over the northern cusp region. The x-axis here, again, in the Sun-Mercury plane, is pointing towards the sun. So on the graph, the 0 point is where the North Pole is. The negative you're going toward the night side, positive, you're going toward the day side. And we see this enhancement around 0, around the cusp, the Northern Pole. Interestingly enough, our results are implying that while the dawn source does match the shape, it doesn't necessarily get to those high amounts of radiance that the actual messenger data gets to. That's not just the case with this orbit. We also looked at a few other orbits. This is 3,483. We see a different case. Again, it doesn't go up to the radiance that the messenger data did, but it doesn't even match the shape this time. One final orbit, 3,231. Again, it doesn't match the shape nor goes up to as how energetic or radiant it should be. But I want to highlight this orbit in particular because we are in the middle of creating a ion sputtering, specifically for solar wind, model of the exosphere for this orbit. Here are some of the results we have so far. Clearly, it doesn't match the pattern at all. But what we can learn from this is that neither the dawn source, which was again the impact vaporization at the dawn, somehow trickling its way to the cusp, and then the solar winds ion sputtering hitting that cusp region, neither of those seem to account for that enhancement that we see in the messenger data. So where do we go from here? Ideally, we are working on building a different model of with the ion sputtering in mind, refining those different parameters to see if we can maybe change the shape. Beyond that, Bepi Colombo can also give us some more observational data whenever that comes online, and we can learn more about why we see this enhancement in the polar cusp region. We can also apply this Nexoplan model, which is what Dr. Matthew Berger called it, to other species and create different model exospheres and see their connection with the different source processes that may impact them and learn how that's connected to the magnetosphere. Here, one possibility is the connection between magnesium exosphere and different magnesium deposits on the surface of Mercury. So what have we learned from looking at the cusp, this region of Mercury, and specifically for its calcium exosphere? Well, so far, our research is implying that neither the dawn source impact vaporization nor solar winds ion sputtering can account for that enhancement that we see. It's very interesting because Mercury is the planet closest to the sun. So we'd assume that if we were to find evidence of sputtering, this would be the planet where we see the most impact. But the fact that we don't see that much impact, and it doesn't account for much of the enhancements, really makes us question what the role of sputtering truly is. But in truth, we simply just don't know. So further research is required to study the exosphere of Mercury and learn about the connection between these different atmospheres, the atmospheric loss processes, the magnetic sphere, and eventually answer that question of habitability. I'd like to thank my mentors, Dr. Amy Merkel and Dr. David Brank, for helping me with the presentation. And then members of the Mercury team that I'm on, Dr. Ronald J. Burbeck and Dr. Caution.
Awesome, thank you. Any questions? It's a great presentation, William. Good to see you in person.
Good to see you too.
I was curious if you could go back to your summary slide.
Yeah.
Like, right, so these conclusions are from like your messenger data sets. Do you guys have any sort of intuition or ideas on whether the importance of sputtering has changed over time? Maybe it used to be more important at Mercury?
Yeah, so before I delve into that, I'm going to make a quick clarification. This is sputtering from the solar wind. It's also very possible that sputtering from planetary ions can actually account for that enhancement that we see, and it's still be very important now than it was before when it comes to seeing these different species in the exosphere. But as far as if it was different as we thought it would be before, and now it's less important, we're kind of limited when it comes to Mercury. We really only have Mariner 10 and then Messenger. As far as space observations go, kind of for ground-based observations, we're limited in species that we can't see because our atmosphere absorbs a lot of that emission. So we wouldn't really quite know, is my guess.
Cool, thanks. Any other questions? Hi, I don't know if you mentioned this thing called pandemic, but what parameters are you solving for with like the longitude integration?
So I'm not too sure how Dr. Matthew Berger's routine works, but from what I've been explained, the Runge-Kutta integration was used to solve the equations of motion that we get to actually create the model exosphere.
Thank you. Any other questions? All right, round of applause.
All right, and with that, that is the end of day 2 and end of all 20-minute presentations. Woo! All right, thank you guys for joining us this year for REU 2022 Symposium. We will be holding an in-person poster session tomorrow at 9:30 a.m. to noon here at SBSC. You can find all this information on our REU website. And again, thank you so much for joining.